Hello, everyone. Sorry for being a couple of minutes late starting off, but welcome to the RAMP Symposium. You should just about be seeing slides on your screen for the first talk of the day, which is going to be delivered by Christopher Payne from Imperial College London. Just a very brief welcome to everyone and a teeny bit of housekeeping. We have a packed agenda and schedule, so we will do our very best to keep to the allocated time slots. We know that a number of people are only able to join for specific talks, so if you're a presenter, please do try to start and finish within the time slot in respect to the other speakers and all of the attendees. So without further ado, I will hand straight over to Professor Christopher Payne. Over to you, Chris. Chris, are you there?
Yeah, I'm here. Can you hear me okay?
Yes, you should see your slides on screen and feel free to go.
Excellent. Great. Thank you. Great. Well, thanks. Well, it's a pleasure for me to introduce the RAMP Task 7. And I'm going to talk briefly about the organization. I'm going to also present some of the modeling as a as a way of kind of describing some of the things that we've been doing and some of the physics involved. So next slide. I should probably say right at the start that myself and Paul Linden are the official leads of the RAMP 7, and we have organized the Task 7, which is entitled Environmental and Aerosol Transmission, and it's one of several RAMP tasks that you can see here. So there are complementary activities related to the pandemic, as you can see here. So next slide. Okay, great. So to organize the Task 7, we decided to divide up the area, the subject area, into several subgroups because it spans such a great range of disciplines, and these are the areas that we've divided up into: exhalation and ventilation, aerosols, aerosol physics, people movement. As you know, people movement can greatly mix the air and have an influence on the dispersion of potentially infected air. Deposition on hard surfaces, deposition, let's say, from droplets from the breath or from sneezing or coughing. Inhalation, it's kind of the opposite of exhalation, if you like, and the case studies. So the case studies, we were thinking it could be used as a way of bringing all the everybody together so all the physics under these different headings could be applied to a wide range of case studies, which include trains, case studies involving people going back to school, people in shops and offices, and so on. So each of these subgroups has a convener, and they're listed on the right here, and they lead the groups, and they report to myself and Paul every few weeks, and we have reported to RAMP every few weeks also. Next slide. On to the next slide. Great. So onto the focus and the strategy. So this is really about how can we understand the understanding of flows within buildings, primarily in order to help mitigate the spread of COVID-19 indoors. And we as a grouping, as a team, we are developing key questions we'd like to address. We're developing, we're investigating key areas and produce a variety of published reports and guidance. Next slide. So this is an example. These are some examples of the sort of questions that we've developed. And these are questions related to ventilation, but this is particularly important as winter approaches and indoor ventilation becomes particularly important. Okay. Next slide. Can we go back? Yeah. So, as you all know, a ramp in its current form has officially ended, but activities are continuing, and there may be a continuation of the ramp activities through the Royal Society, but that's to be determined. But these are the kind of activities. So there are various teams that have been formed and networks. For example, the TAPAS network that is dealing with air pollution in schools, but much of that is associated with is applicable to COVID. So that's a current major issue. There are several UKRI projects that have been developed by the various teams, and there may be the Royal Society could be viewed as a conduit for policy, as well as helping to provide the focus of this work, and to bring everybody together, and so that we all work as a team, and we're not just focused on our own specific areas, but we are aware of the importance of our individual subjects, let's say. To the next slide. Okay, so I'm just going to give you a very brief summary of some of the modeling. So this is an example of ejector from the mouth, and we can see here a mesh that's used to resolve this ejector. Can you click on the slide, see if there's an animation? And you can see here, we can see the mesh that's used to resolve the resulting turbulent flows and ejector, which you can just see. And if you click onto the next slide, hopefully you'll be able to see that through the animation. So you can just see the ejector as droplets being generated from the mouth, and in the bottom right you can see a mesh that's focused its resolution to resolve that ejector, or the formation of droplets. Onto the next slide. So as you know, or as you may know, that the droplet and ejector can be highly uncertain. The droplet size distribution from the breath, or sneezing, or coughing can be highly uncertain. So a possible way of dealing with this is using data assimilation methods. So we are currently investigating the use of data assimilation to initialize some of our transient models, like the models you've just seen. So, okay, can you click on that? Oh, okay, the animation is not working. Okay, so onto PPE.
Just 1 minute left, Chris. Thanks.
Oh, okay. Onto PPE efficacy. We've been working quite hard on face masks. So looking at the pore scale structures, Click on next slide. Okay, and looking at the flexible fabric as well, and the interaction between the fabric and the flows. Next slide. And looking at flows within our transport systems. Click on this, and in this case, it's an animation of. Can we go back and click on that? Animation of flow within a train carriage, and you can see effectively the CO2 rising to the roof of the train carriage. Next slide. And producing things like risk maps is key, and we can see a risk map here on the right. Next slide. And ventilation in buildings is also key, and being able to resolve the resulting flows and CO2 distributions and temperature distributions in our building environments, our buildings can be very important. This is an example of flow in a very large in a series of flats, 96 flats within coupled to an urban neighborhood environment. Next slide. Next slide. Go back. And these are some examples of, go forward. This is an example of some of the geometries that we're working with for shops and schools. And this is just the geometry generation. We're working towards running these simulations. Next slide.
Just conscious of time, Chris. Is this a good place to stop?
I just a couple more slides. Go on to the next slide. Obviously, very important to make a connection with experiments to validate the modeling. Next slide. Next slide. Less important is the outdoor modeling, and which we've just seen flashed up in front of us. Okay, because of the ventilation in our urban environments, turbulent ventilation. Next slide. And we have also reapplied some of the machine learning methods that we developed within this to model the spatial distribution of infections. Next slide. Okay, thank you for listening, and I hope you enjoy the meeting.
Thanks very much, Chris. If I can squeeze in one very quick question which has come in, which was to do with the LES simulations you showed, and the mesh appeared to be moving, the comment says, and is that correct? Do you want to just comment on that?
Yeah. So in most of the simulations I've just shown, we're using an adaptive mesh which focuses its resolution on the important parts of the flows. Let's say it doesn't actually move, but we recalculate a mesh and optimize the size and shape quality of each element in the mesh to optimally, in some sense, represent the physics.
Thanks very much, Chris. So we didn't quite keep to time, but I do know that Paul Linden, who is chairing the session, is now on the call. Paul, did you want to take over?
Yeah, thanks very much, Owen, and thank you for standing in for me. I'm sorry, I seem to go to the wrong meeting for some reason. But let's move swiftly on. So the next talk is by Pedro de Oliveira from Cambridge. Perhaps you can share your screen, Pedro, or put your slides up on suspended viral dose. And this is a mixture of work on subgroup 1 and 2.
Thank you very much, Paul.
Take it away.
So in this work, what we tried to do was to provide estimates of the evolution of the droplets emitted by a sick individual to understand the transmission modes of the SARS-CoV-2. So from early in the year, we followed how the debate around the spread of the virus shifted from droplet transmission towards aerosol transmission. And finally, in April, a letter was published at the Journal of Hospital Infection that got a lot of traction, and some media outlets were all raising the concern of aerosol transmission. So what we tried to do from around that time was to use a straightforward model to approach the transmission problem as a continuum between droplet and aerosol transmission. So we saw from the pioneering work by Wells in 34 that we know from this work that small droplets evaporate very quickly and large droplets fall without much impact from evaporation. But it was only recently that scientists were able to measure the whole range of droplet sizes and also characterize the gas flow rates involved in a respiratory release. So now we have the information we need to model the problem, but just last year, Marr and co-workers pointed out that the droplet composition may have an important impact in its settling time. And this could also account for a high uncertainty when modeling the problem. So here we provide some insight on the timescales and the position rates between short time scale problem of droplet transmission all the way to the long time scale problem of aerosol transmission. So before I show the results, I'd just like to acknowledge my co-authors, Dr. Léo Mesquita, Savas Gantonas, and Professor Mastorakos at Cambridge, and Dr. Andrea Giusti at Imperial. So also, the paper is under review, so please bear in mind that this is a scientific exercise for us to understand the big picture of transmission, and you'll see today how specific details of each problem, as ventilation, for example, may also have a big impact on viral transmission. So we model the motion of sputum droplets individually, and the evaporation is computed with a well-established model. We account for the effect of droplet composition on the vapor pressure by taking 3 droplet compositions. The composition is similar to nasal surface airway fluid with a low protein content, the composition of aerosols formed in breath that has a higher protein content, and also pure water. So size and number of droplets escaping the mouth are taken from the BLO model, considering droplet sizes from 1 micrometer to a millimeter size. And for the virus, we take an exponential.
Interrupt, Pedro. We're still seeing your front cover slide. Are you sharing the correct screen? We're seeing the slide with the thumbnails down the left-hand side.
Oh, that's a shame. Apologize for that.
So I'm now seeing your. Oh,
no, we're not seeing any. Yeah.
1 second. Okay, let me try this. Are you seeing this now?
Yeah, we can see this now. You just need to go to full screen though. Can you do that?
We're seeing the screen that's got transitions, no transition effect, add an effect on the right-hand side of it.
Transition. I apologize.
Yeah, I'm on slide 3, motivation, but it's
yes.
But it's in sort of editing form, not in play mode.
Okay. Are you just seeing a bar on top of it? Do you mind if I leave it that way?
It's fine like that if you, yeah, it's fine like this, I think.
Okay. I'm sorry for that.
That's okay.
So it didn't miss much. There was just this slide. And right. So as I said, we model the droplets. We use a well-established model. We take into account the effect of composition, 3 compositions for the liquid with basically as pure water, low and high protein content, and we take an exponential viral decay for the virus with different viral loads as found in the literature. So basically, we release droplets from a 1.5 meter height and let them evaporate and settle by gravity. So here we're looking at the evolution of number and mass of suspended droplets relative to its initial values.
I'm still looking at the same slide, label, number 3, labeled innovation.
Ha.
That's, well, now we're at 5, number 5, yeah.
Okay. I'm very sorry. Let me
It's okay.
Try to change the for some reason I cannot change to the full screen mode.
Okay. Well, as
can
long
you
as
see
we
the full screen mode now, Paul?
No. I can still just no. Well, sort of. It's got bigger. I mean, it's, it's just that you haven't been advancing the slides.
Yeah, that's very odd. I don't know what's happened. It's worked in the trial before, so just carry on like that so we don't get more delayed. So if I change it like this, you can see it, right?
You're on 6 now. Yeah.
Yeah. Okay. So, so very roughly, the total suspended mass decays more or less the same way between speaking and coughing. This is because the position is controlled by large droplets, and these large droplets between 100 and micrometers to 1 millimeter, they account for 99% of the liquid mass. So plotting that into a log scale, we can now see the differences between speaking and coughing and relative humidity in that yellow bit that I highlighted there. And this is associated with droplets now in a mid-size range between 30 to 100 micrometers, and those have very similar evaporation and deposition time. So that's why they impact the decay. In the paper, we also give the evolution of size distribution of the suspended droplet cloud, which can be particularly useful, for example, for ventilation calculations or design of sterilization equipment. So if we take now the aerosol as defined by the World Health Organization, we see that early in the beginning, there's an increasing number, but right after the mass of the droplet cloud drops, and after 1 hour from speaking, there's barely been any change in any deposition in the mass of the aerosol. So to consider the effect of composition, we see that a single droplet with a low protein concentration, so that's the lower band in the yellow, evaporates down to 20 to 30% of its initial diameter, depending on the relative humidity, while a high protein droplet evaporates down to 40 to 50%. That's the top band in the figure. So this effect of the equilibrium diameter results in a large difference in settling times, and as we can see in the B figure here. So if we consider the whole range now of droplets, this effect applies to droplets up to 50 micrometers. That's the line here. And for these, the settling times can vary by almost 100% as a result of composition. So in terms of calculating aerosol removal by ventilation, the different settling times won't really make a difference, but still some uncertainties can be introduced when estimating the mass of the aerosol that must be removed by ventilation. So one might be tempted also to neglect the effect of droplet composition on the short time scale problem of droplet transition, but it turns out that these impact also the mid-size range droplets, and that can have an effect on the droplet reach too. Okay, so we plot now let me just zoom out a little bit. The decay rates of the suspended viable viral copies or plaque forming units. For reference, we consider a single short cough and also a 30-second speech, as both have the same associated mass and virus. So we take, let me clean up the slide a little bit, we take 10 to the power of 8 copies per milliliter, which is highlighted in blue, and also a much higher viral load, which is 10 to the power of 11, which corresponds to a severe stage in disease, so in very extreme conditions. I should add also that the initial viable viral load could be lower by 1 or 2 orders of magnitude, but I believe this hasn't been measured yet. Let me say, the infection dose refers to the amount of suspended viable virus, but if one wants to model the inhalation and exposure time to such load, this could also be done. So one of the key differences in the decay of suspended virus emitted from coughing in comparison to speaking can be seen in the long time scale. So for the high viral load, gravity removal and viral inactivation will only bring the total amount of viable virus below a value needed for 100% infection in about 1 to 7 minutes. So that's the bar we see in the top figure. For coughing, that's the case, but depending on the droplet composition as well. And for speaking, that's the two figures at the bottom. We see that around 30 minutes are needed for the same reduction in the suspended viral dose. So mind that we're talking about a 30-second speech here. So due to these small droplets produced in speaking, these doses can be suspended for over an hour. So this is approximately the half-life of the virus, as we know. So now just quickly, I mentioned two implications of these figures. First, in order to keep to the time, I'll just mention the two. So uniform velocity, if we assume a uniform flow, we can say for a distance of 2 meters for a background flow of ½ meter per second, which should be the case if you have some air conditioning unit. You can neglect the effect of the exhaled gases in this case. And if we run the calculation, you see you have 4 seconds more or less of time of flight between point A and point B. So from the emission source to the receptor, and that would account for 20 plate forming units at the receptor. And if, for example, we have some induced upward flows, which could be the case in heating or also as a result of air conditioning, this could increase the reach of some mid-sized droplets and could bring the risk of infection at a much higher value. And just to close up, in the case of no background flow, we then have to consider the high velocities at the mouth, as Professor Payne just showed in his presentation now. So in this case, we can approximate the problem of coughing as a continuous route jet in stagnant ambient air. In reality, we know the emission is not continuous, jet is buoyant, but as an approximation, if we take these parameters for 2 meters distance, we have that time of flight is just below 1 second. So we see here in the plot, and taking the suspended viral dose for that would be 2,000 platform units, which is way above the limit for 100% risk of infections. So safe levels here are only reached after 30 seconds to a minute. So that's for a single half-second cough. So it shows that an unprotected cough is not safe at a 2 meter distance without a mask. And the same goes for a quick chat. So I hope I didn't go too much over the time. I apologize for the delay. Thanks very much for listening.
Well, thank you, and thank you for keeping to time given the technical issues. So appreciate that. And we have time for a question or two, I think. Owen, are there any in the?
I think we're up to time, so if we skip questions on this one, but just to remind all of the attendees, please do type your questions in the window and we'll come to them at the end of each talk.
Okay. All right, well, we'll move on then in that case. So the next talk is by Michael Short from the University of Surrey, and it's on subgroup 4 on SARS-CoV-2 fomite transmission and surface survival. So please go ahead, Michael, when you're ready.
Thank you very much. Can everyone hear me?
Well, I can hear you, so I think that means yes.
Yeah, great. Well, thank you very much. It's a pleasure to speak at the symposium. I am Michael Short from the University of Surrey. I'm a chemical engineer, so this is kind of a new topic for me. We've been working on this since early April with all of these colleagues from universities all around England. It's been fantastic to be involved in this. I'm going to jump around the topic a little bit because we have a number of projects working on kind of small little things, and I'm kind of trying to represent the work going on throughout the group, and we've been meeting to discuss all of these different projects. I'll start with talking about what we know about how the virus survival on surfaces, and then we'll move on to some of our modeling work that we've been doing. Okay, so we know that the virus definitely gets transmitted to surfaces via droplets, via fomite transmission directly, so from the hands onto surfaces. These are two studies in hospital wards that have patients in them with infected with SARS-CoV-2, and you can see that the number of positive cases is, you know, between, I mean, the number of PPE items that have been infected from the hand sanitizer dispensers and the gloves and the eye protection is up to, you know, 20% of the items. And then on surfaces within the ward, there are a lot of surfaces that are contaminated. So 60% of the samples of the floor, for example, were contaminated with the virus in some quantity. So we know that the virus definitely does get transmitted to surfaces. The factors that affect the survival on the surfaces include what type of surface it is. More stable surfaces tend to have longer survival times than rough surfaces. Ambient temperatures definitely have a strong effect. So stability decreases with increasing temperature, meaning that at low temperatures, we've got the virus survives for far longer times. Humidity has a big effect. So stability decreases with increasing humidity. So having more humid rooms, especially in winter, might help with stopping the transmission of the virus to a degree. However, too high humidity can also cause health issues. So this should be done with, you know, some level of caution. SARS-CoV-2 is also very stable between a high pH range. So trying to change pH doesn't really help to kill the virus. Now these points with the stars they're based on studies with other coronavirus strains. So we know that sunlight and UV are potentially disinfecting. We know that for viruses in general, like flu, it has a very strong effect, just plain sunlight. For UV, there's been less study on SARS-CoV-2 specifically. I think there's a talk on that later. But for SARS-MERS, it does have a strong effect for UVC light. So we think that it is very likely that this will have a strong disinfecting effect. The method of contamination has also been shown to affect how long the virus survives. So if it's a dry fingertip that infects a surface, or if it's a droplet, this has an effect on how long the virus will survive, as well as the concentration of the virus in inocular. The droplet size also does not really affect the stability of the virus. So, this is by now quite a famous graph from Van Doornmalen, and they basically show that how the virus survives on different surfaces. So, for example, in aerosols on the far left, you can see that the virus survives fairly well over the course of 3 hours. And on different surfaces, this changes, with plastic being where the virus survives longest, with half-lives of 7 hours, more or less. So that means that after 60 hours, there are still some infective virus cells on surfaces. While the study was done with a lot of inocular added, so far more virus was put onto the surface than would be deposited naturally, this still shows that there can be virus living on surfaces far after an infected individual has been in a room. We also know that there are a number of, we know about cleaning. So obviously it's very difficult to clean the air, and it's very difficult to control how other people behave. So if they're washing their hands and wearing a mask, however, we can clean surfaces. We know that alcohol is a very effective at inactivating the virus. Formaldehyde, sodium hypochlorite, hydrogen peroxide are all good cleaners. Chlorhexidine, which is a cleaner used in dental practices and some medical facilities, is actually ineffective at killing the virus. So soapy solutions potentially disrupt the virus, and there was a lot of talk about the lipid layer and soap and all of this, but actually a study has found that SARS-CoV-2, infective SARS-CoV-2 can still be detected after 5 minutes of incubating with hand soap. So while soap is probably a good idea, because you are physically removing the virus in a lot of times and putting it into, you know, into the solution, it's not necessarily the greatest if you're going to be disinfecting surfaces and those sorts of things. So now we move on to some of the modeling work that we've been doing. Piotr at the University of Bath has been working on this model with basically using the Arrhenius equation to model how the virus survives on different surfaces at different temperatures. So the Arrhenius equation is known to chemists all over the world as the way that we relate rate constants of reaction rates to temperature. And in this model, basically trying to do the same thing. And you can see that it fits fairly well with the experimental data. And you can do this on many different surfaces with specific parameters that you basically fit. And Piotr has also looked at using this model with humidity as well. Alison has been looking a lot at how we model the droplets on surfaces. So evaporation of water droplets, of pure water droplets on surfaces occurs very rapidly in the order of seconds. But saliva is more complex and affects the evaporation. So it's a stable mixture of water, enzymes, proteins, and electrolytes. And then we kind of go into the field of conjecture here, because there are not a lot of materials properties available for these types of things. So we were looking at things like, does a protective layer, outer layer form? How long until the saliva crystallizes? How is virus survival changed over time? What are the appropriate material properties for these models? For smooth surface rather than a groove, does this droplet detach from the surface more easily under cleaning? Is the droplet more easily transferred from surface by finger touch, etc.? This work didn't really go very far because of the lack of information, but there's some pretty pictures. So most of our work in the group has been on surface transmission risk modeling. So the goal here was to propose some framework for estimating the risk of infection by, in enclosed environments via fomites and the air in some of the models, allowing us to study mitigation strategies, common environments, and to quantify the various transmission pathways. So, for example, we have this pathway here where an infected individual touches a public object, and then that public object is handled by somebody else, and somebody touches their face. So the key elements in the framework is human behavior. So we model this either using Markov chains or average touch frequencies based on empirical data. So for example, we have some studies that have been done in graduate student offices, or in, we have CCTV cameras in trains and so forth. So we can use these human behavior parameters within the models. We have decay models describing virus inactivation, for example, by temperature or just by time on different types of surfaces. We have transfer efficiencies describing the amount of the virus that's transferred during each contact or during deposition, average deposition rates by a person that is infected at a certain rate. And then we have dose response models. So that estimates the infection risk based on the corresponding dose that is given, although these are all highly uncertain parameters within the model. The applications here is to compare different disinfection strategies and also check the effect of the number of occupants inside of a room, the behaviors of people, etc. This work is from Marco-Philippe King from the University of Leeds, and this deals with fingertip contamination. So at each time somebody makes contact with the infected surface, how much of the virus is transferred from the surface to the fingertip. In this model, we have basically a concentration gradient between the surface and the fingertip. And the fingertip basically, as the fingertip touches the surface more times, it transfers less of the virus as it becomes almost, let's say, saturated with the contaminant. In this case, it's E. coli, but we know that the transfer efficiency for influenza is about 7%. So SARS-CoV-2 is probably about the same, but this model works fairly well at describing this phenomenon as you make more contacts, how much of the virus gets transferred to the fingertips.
You have about 2 minutes left, Michael.
Thanks. Their group also did some work with viewing how people interact with different, how healthcare workers interact with the environment to develop these transition probabilities. And we basically see that with different types of care, you have different chances of interacting with different objects within the room. And then you can use these to generate sequences of contacts from transition probabilities. So for example, from one patient to another and to different equipment. And finally, the model that we've been working on at Surrey mostly has been this fomite transition pathway model, where we have basically all the transmission routes are represented within this diagram. So we have air and fomites within a space. So for example, desks and the air. And we have different deposition rates from the air to the fomites, and from hands to mucous membranes, from hands to fomites if infected individuals, and we can have many people inside of the room at one time. A lot of these parameters are quite unknown, but we can use this to see the quantities of the different pathways. So this is a quick case study with basically somebody's working a day in an office from 9 to 5. There are 3 items in the room: a door handle, a desk, and a paper. And he has a meeting with an infected individual. So these are a lot of estimated parameters, but it gives you an idea as to what we can do with the model. So for example, the viral load on the objects on the left is when the individual enters the room, he starts infecting the different objects, the desk, the door handle, and the paper. And then after the meeting ends, we either disinfect on the right or we do not disinfect. And we can't disinfect the paper and we can't disinfect the air. So that's why those 2 curves remain the same. And then we can model how the individuals interact with those surfaces. And so we can see that the viral load on the hand of the individual, if you wash your hands, so on the right here, he washes his hands after the meeting, but he still increases his viral load on his hands because he's interacting with the paper, which we did not wash. And then we can also add the viral load on the mucous membranes of the susceptible individuals, and thus basically this then gets translated to your risk of infection. So this is the risk of infection if you included cleaning or not cleaning the surfaces after having a meeting with an infected individual for 2 hours. So you can see that by cleaning those surfaces, our relative risk decreased by 40%. A lot of these parameters are unknown, but that kind of gives you an idea of the flavor of this model. Yeah, so thank you very much, and I'm happy to take any questions.
Yeah, thank you very much, Michael. Do we have any questions, Owen?
Yes, there have been some good questions coming in. One is from Pawan Gildial, who's asked, on the slide where you had the model of virus inactivation, you showed the shortest lifetime on the paper or tissue paper and the longest lifetime on steel and plastic. Does it mean that if we make masks out of paper, that's most effective?
Well, it depends what you mean by effective, because there have been there's been a lot of anecdotal evidence from a number of hospitals where people are getting infected, not actually by transmission of the virus with the patients, but via fomite transmission afterwards. So this means that they were basically, when they were taking off their PPE, they made some mistakes, or they had papers that they then moved from the hospital wards into the offices, and then people in the offices weren't taking precautions. So it depends. I mean, you obviously, if you mean that you just want to leave the PPE lying around somewhere for a certain amount of time and then be kind of confident that it hasn't been infected, then sure, making PPE out of paper is a better route. But it depends, because if you're talking about fomite transmission or whether you're talking about the effectiveness of the PPE itself, that's a different question.
Thank you. I think we have time for just one more question. Maybe while, if you stop sharing your screen, Michael, you can continue to answer. And Andy, you can set yours up if you like.
There was a follow-on question from that then, which is, are you modeling resuspension of fomites into the air?
This is a really good question. We have been thinking about it, but again, it's so difficult to find parameters for these things. Obviously, we've built this framework that we can kind of, I showed you that diagram with all the little arrows between all the different pathways, and we can have the arrows going both ways, so we can have deposition and we can have resuspension. But the question is, what do these parameters look like? So putting them in the model is easy. The question is how much actually gets resuspended from the surfaces, and we actually need that information to so it's difficult to tell. So this is where we're kind of looking at the more, let's say, macro aspect, whereas some of the other people in this symposium are looking at those more micro levels. And if the people looking at those aspects can sort of inform our models, that'd be fantastic.
Thank you. Yeah, thanks very much, Michael. We must move on now.
Sure.
So I'm going to move on now to Andy Woods from the BP Institute in Cambridge, who led subgroup 3 on the role of people movement. So Andy, over to you.
Oh, thank you, Paul. So yeah, thank you very much for this opportunity to share some of the work we've been doing looking at the role of people movement on aerosols and aerosol dispersion in buildings. And we had quite a small group, but we've done quite a lot of new work trying to understand how aerosols move around in buildings. So I thought in this talk I'd just present some new data on CO2 mixing in buildings which provides an analog for the motion of some of the very small aerosols. Particularly, I'll look at data from Papworth Hospital in Cambridge, and then I'll present some new experiments, analog experiments in the lab, and talk a little bit about the impact in supermarkets, transport and queues. And just to note that Edwin Galea at Greenwich has also been doing some numerical models that complement a lot of this analytical and experimental modeling. So I need to get, there we are. So on this first slide, just for context, this is the new Papworth Hospital in Cambridge. And in a typical patient room in this hospital, there's top-down ventilation, very strong air conditioning. Air comes in and then leaves through the ceiling as well. And this leads to quite a lot of mixing in the space. And by injecting clouds of CO2, such as shown by the red star on this little plan of the building in the top right-hand corner, we were able to monitor how that CO2 spread through the space. And this graph here shows the data from a series of sensors monitoring that CO2. And what we see is that within about 200 seconds, most of the sensors have very similar values, and then they decay exponentially. And this shows you that this room becomes very well mixed. And so the ventilation flow itself is mixing the air and the aerosols. And the very fine aerosols have fall speeds, and I know Pedro's given a much more elegant and detailed description of the fall speed, but just as a scaling argument, we can see that these very fine aerosols, less than 5 microns, take over 1,000 seconds to fall out, order 20, 30 minutes. And on that time, we're actually seeing the ventilation coming in and the concentration decaying right down of the CO2. So the CO2 is acting as a proxy for these very small aerosols. And I guess what we're seeing is the room becomes very well mixed. And I just thought I'd put in some data from a lecture room in Cambridge, which we've been studying, where again, this is about 20 meters by 20 meters in size. And we have a series of sensors shown by these color symbols. And again, both the sensors on the desks and the sensors in the walkway of this lecture theatre all show that within about 200 to 300 seconds, the CO2 released at the front of the lecture theatre becomes well mixed and then decays exponentially. And so I guess the message is that in many rooms, the aerosols become well mixed. And a little lab experiment we carried out in a water bath where we injected air or water at high level with some blue dye in and then extracted the water shows that both the ventilation air in blue becomes mixed, but also if we have a heat source or some source of buoyancy, that also becomes well mixed. And both of these lines show this exponential decay. And so in a number of small spaces, we would expect the air to become reasonably well mixed. But one of the outstanding questions relates to corridors or long walkways, because if each of these rooms is well mixed and you open the door, you may expect to get infection or aerosol coming through the doorway and then moving down the corridor. And so we've had a look at the way the air mixes in corridors, and of course there can be ventilation flows, but also if people walk up and down the corridor, that has a big impact in terms of the weight behind people. And so we did some experiments in Papworth where we looked at releasing a pulse of CO2 at one point in the corridor and then monitoring how that CO2 spread down the corridor. And the black line shows 3 sensors that are about spaced by 10 meters. And again, after a short time, they become very correlated and they decay away with the ventilation. But when we walk up and down the corridor, and this was at the frequency of every 30 seconds walking up and down the corridor, you see that the residence time of the CO2 is much longer. And it's because it keeps on mixing with new ventilation there in the corridor. And so we've done some experiments to try and understand the mixing in a wake associated with people moving. And so we have in a little lab experiment, we have a channel, and we put a cylinder in the middle of the channel and just move the cylinder back and forth. And these are high Reynolds number experiments. Here's a false color movie, just showing the motion of the cylinder back and forth. And there's a parcel of dye in the center of the tank. And what we see is as the cylinder moves back and forth, this parcel of dye becomes mixed in the wake of that cylinder. And after several passages of the cylinder, over a few hundred seconds, we'd expect to see this dye spread out. And in fact, if we analyze the data, then what we find is that here's just a time series from the experiments showing that the dye spreads out along the channel. And if we look at this in false color, we can see it in more detail, the way it's spreading. And this is now the length of the channel, and we're just seeing with time going along this axis, we're seeing the vertical average of the dye at each point along the channel. So this is the length, here, and this is the vertical average concentration. And what we see is, as time goes forward and the person moves back and forth, the cylinder moves back and forth along the channel, we're seeing this cloud of dye spreading out along the channel or the corridor. And this spreading suggests that it's a diffusive type or dispersive type process, where we'd expect to see a Gaussian spread of the concentration. And indeed, that's what we see in these graphs, where we plot the concentration as a function of position relative to the center of the cloud. And the diffusivity is actually very large. It's of order about 0.1 meters squared a second. And so this shows that people moving actually can cause enormous lateral spreading of the aerosol over and above the ventilation flows and other flows in the space. And we've now been looking at experiments where we release clouds of particles in a tank and do the same experiments. And so the particles actually sediment out. And so this is now modeling either the ventilation or the settling of the aerosols over the time of the mixing. And so we see now the cloud starts spreading, but then it decays again as the particles settle to the base of the tank. And again, these collapse to the same Gaussian profile, but it's now exponentially decaying in time. And so we have a model for how this spreads. And so we've been then looking at the role of ventilation. So here's a movie showing a tank. The top panel here is a tank full of particles. And we have a cylinder moving back and forth, and then a net ventilation flow coming along the channel from left to right. And what you see is there's a wave, a sort of clean wave coming through, the clean air coming through, but there's a lot of mixing going on because of the cylinder. First of all, keep the particles very well mixed vertically, and secondly, actually cause some back mixing of the particles. So the air here, which is being ventilated, is actually being contaminated with the particles from down here. And so again, this is showing the really important role of the mixing in people's wakes in terms of increasing the residence time of aerosols and dispersing them along a channel. And here's just a time series showing position and the color is concentration, the time on the vertical axis, showing the aerosols being wafted downstream in the ventilation flow, but they're mixing here because of the people moving. Let's move to the next slide. In order to try and take this model and try and do some more predictive assessments from this model, we've developed an individual person mixing model, which has been calibrated with these experiments of the corridor. So that if we have an irregular stream of people moving down a corridor or moving through a space, we can actually account for the mixing associated with each of those people and then get a cumulative model. So here's a little calculation where we have 3 clouds of aerosol that have been released by breathing, and then we have a stream of people by these little red dots moving down the channel. And here's a little movie showing these people moving down the channel, and these clouds of aerosol are being mixed up as a function of people moving down the channel. And you can see here how the concentration is decreasing in magnitude and spreading in distance along the channel. And one of the implications of this sort of modeling is that if we're in a supermarket or in an underground tunnel or or in a queue going into a lecture theatre, for example, and there's an infected person who's breathing out every 2 or 3 seconds, if you're walking along at 1.5 to 2 meters a second, those breaths may be spaced by 2 or 3 meters. And so initially you're going to have localized high concentration, relatively high concentration clouds of aerosol. But as more people come past, those clouds are going to get mixed and dispersed. And so we've worked out the effective dose that you might experience if you walk down a corridor. So here's an infected person moving down a corridor, and there's an initial series of clouds that then get mixed up in the diffusive wakes of everybody following. And so the first people who are following an infected person see quite a lot of variability. This gray zone models the variability in the dose they may receive, because they may or may not breathe in one of these infected clouds. But later on, where the wakes have mixed the aerosol through the space, this variability really decreases. And so even though the dose has gone down, there's much more predictability about the size of that dose. And at the moment, we're applying this to look at this impact.
About 2 minutes, Andy. Sorry to interrupt.
Yeah, I think that's my last slide. So just to summarize, in this group, we've been looking at the transport of small aerosols. We've seen they're transported and well mixed in spaces by the airflow, but people have a significant impact on that, on the mixing. And the residence time of aerosols may be tens of minutes. So you can reduce the exposure to aerosols by, I guess, following a lot of the guidelines that have been brought in, but we can understand reasons for limiting occupancy numbers, limiting interaction times between people, wearing face masks, and increasing the ventilation rates in buildings. So I'll finish at that point. Thank you.
Yeah, thank you very much. So do we have any questions, Owen?
There are quite a few questions on this one. The first one to come in was, in the time series of flow along the corridor, what size were the particles that you were modelling?
So in the experiments, we were releasing clouds of CO2 in Papworth Hospital, and we were actually monitoring the concentration of CO2 at different positions along the corridor, both at head height, but also at high and low level. In the lab experiments, we're using very small silicon carbide particles with a full speed that's calibrated dimensionally, so it's comparable to the full speed of the very small aerosols. So they fall out on a timescale comparable to the ventilation time.
Perfect. And in reference to the same study, the ventilation you showed when it was from the left to the right of the model, how would it work if the air was brought in, delivered with low velocity at high level and extracted at low level? Would that move the contaminant away from the breathing zone more quickly, and would that then be better?
So I think if there are people walking along the corridor, that has a dominant impact on the way the aerosols and the air is mixed up, as you saw from the data at Papworth. But what we found at Papworth in the flows driven just by the air conditioning system, there's extremely variable airflow speeds. So near the inflow grills, there's very high speeds, and that then diffuses out. And in other parts, there's much lower speeds. And so I think there's a number of different effects that cause the air in the space to mix. And we actually found a convective recirculation, very strong recirculation occurring in the corridor because of entrainment in these jets. And so I think it's just the background airflows are more complex than just having a simple arrow pointing in one direction. And so our lab experiment is a very idealized experiment compared to the flows in real buildings. So I think I'd be cautious about thinking there's just unidirectional flow. There's much more convective mixing occurring in every building we've measured.
And there's a follow-on question from that, which is, given the results, what would you recommend for the ventilation of, say, that corridor in the Papworth Hospital? Would you recommend that the flow rate be designed from the corridor to the room, or from the room to the corridor?
So at Papworth, so the corridor has its own inflow and outflow vents, and the rooms have their own inflow and outflow vents. And I think our recommendations there were that you keep the patient doors shut as much as you can to limit the transmission across the doorways, and so actually trying to separate the different spaces. The actual dispersion of infection in the corridor is very hard to stop if you have a busy hospital ward where people are moving up and down the corridor. So the other thing is to actually limit the time between successive passage of potentially infectious people. So this was a cystic fibrosis ward, it wasn't just for COVID, where different patients have different illnesses and so you'd actually allow for a ventilation time to occur before the next patient, vulnerable patient, goes down that corridor. But I think separating the space is very important.
Okay, thank you. I think at the time we should draw this to a close. We have a 5-minute break, and I think this is a moment to do that. Please don't leave the webinar, but just we'll reconvene at 10 to 2. So in a bit less than 5 minutes now, but just time to stretch your legs if you want to. Okay, everyone, that was a quick 5 minutes, I'm afraid, but we're now back on schedule. So we'll move on now to the second 4 talks, and the first of which is given by Henry Burridge from Imperial, who was the lead of subgroup 1 on wintertime ventilation 2020, and you can read his title. So over to you, Henry.
That's right. Thank you, Paul. So I'm going to talk about ventilation in the context of winter 2020. Thank you. The first question to ask in that context is airborne transmission significant? The answer is we can't be 100% certain, but the academic community has really moved heaven and earth to evidence that it in all likelihood is very significant, and that's only going to increase in winter. And you know, the overriding message is that we will have to consider all transmission routes, and airborne is one of them. My slides are moving very slowly. So we need to think about how to mitigate airborne infection, and the most obvious thing to do is just increase the supply of outdoor air. So just increase the ventilation, and that's really led to the guidance this summer to do so, and do so by increasing your ventilation system performance and opening windows and doors, etc. But in winter, that brings a conflict between doing so to reduce risk whilst maintaining comfortable temperatures indoors and managing people's energy bills. And so really we need to understand what is adequate ventilation for winter 2020, and so we start to think about modeling the airborne infection risk, and that is can be done using the Wells-Riley approach. And the greatest uncertainty in such modeling approaches is how to parameterize the modeling input, the quanta generation, and this value Q depends on the disease. It varies with disease, and it varies with respiratory activity and physical activity. So me talking is not a good thing, and if I was walking and talking, it would be worse. The crucial thing is that I'll show results using values from the published literature based on SARS-CoV-2, and we'll show some results for varied activities and the associated quanta rates. The work we've carried out is really based on the extension of Rudnick and Milton, who very insightfully argued that to become infected by the airborne route, one has to breathe air that has already been breathed by an infected person, and we can monitor rebreathed air easily by CO2. We're the dominant source of CO2 in most buildings, and the framework of their model requires a constant occupancy, and crucially you have to specify a duration over which you're going to assess the risk, and if you increase that duration, you increase the risk, and that you have to set some arbitrary cutoff. So we thought very carefully about this and thought, well, how can you decide if indoor space contributes to the spread? Well, it contributes if an infected person keeps attending a space while they remain pre or asymptomatic, and during this attendance they infect somebody else. And this period is about between 5 and 7 days for COVID-19, and it's not typical that we constantly occupy a space for the period of about a week. But we realized that there are indoor spaces where the same group of individuals return each day, week in, week out. So it's helpful to think about these regularly attended spaces, and they are, for example, school classrooms and open plan offices. So we need a model that enables the people to leave and come back over the period of a week. So in our model, we look to consider one pre or asymptomatic period. That's a working week. We can either use monitored CO2 data and occupancy profiles, or we can create simplified models of the indoor spaces and the usage thereof. The result of the model is that we can rigorously define the expected number of airborne infections that arise from an infected person attending work or school and coming every day to the classroom or office whilst they remain asymptomatic or pre-symptomatic. So first of all, some results for a modelled office. This is a modelled office suitable for about 40 people. We let people arrive during the period between 8 and 9 in the morning. They all leave the office for an hour at lunch, and then they all leave sometime between 5 and 6 in the evening. So then we can look at the likelihood of infection, and here we see on the horizontal axis the time in days. So this is one pre or asymptomatic period, and we've got an adequate ventilation rate for an office according to SIPSI Guide A of 10 litres per second per person. And if we take the sort of values that are expected for quiet desk work, that's the red data, over our period of a week, for an infected period, a person is attending the space, there's about a 1% chance that somebody else gets infected. It's less if we assume COVID-19 is less infectious, obviously, but crucially, if we just change the activity from quiet desk-based work to talking, so for example, a call center, then the risk really rises quite significantly, in this case to about 5.5%. We can also look at the effect of ventilation rates. Again, our base case, the red data, and if we double the ventilation rate, we decrease the risk, and obviously if we have inadequate ventilation, and this is a ventilation rate not atypical for school classrooms, then we see the rate rising to a bit over 2%. If we're worried about the role that an assumed value of quanta has, we can take out the sensitivity by looking at the relative risk. So we can just sort of say our office has this provision or our school classroom has this provision and examine scenarios around that. And we see that we're relatively insensitive to the duration, which is a nice result. This table I include because the slides will be available afterwards. But this is our base case, adequate ventilation with quiet desk work, and we expect about less than half a person to get infected over a pre or asymptomatic period. If we're in a call center, things get far worse. We're starting to infect 2 people for every person that gets infected. So that is bad news, and we can ventilate hard and get around that if possible. The last 2 rows show quanta rates for sort of so-called super spreading events, and there, if you have a super spreading event in a regularly attended space, a single infection leads to a very significant number of new infections. As I said, we can use our model on monitored CO2 and occupancy, and this we have thanks to the MAGIC project, and they examined a small office typically occupied by around 6 people, up to 6 people. Here we show results from 2 days, the 29th of September on the left and the 5th of October on the right, happens to be 2017. Top pane shows the occupants coming and going throughout the day, 0 to about 5 being a typical occupancy, with this spike where 22 people visited. The crucial thing is that on the 29th, the windows remained open, and on the 5th, the windows remained closed. And so what we can see is that when the windows were open, CO2 doesn't build up nearly as much as it does when the windows were closed. And our modeling allows us to assess the associated risk. And we see that on the day where the windows remained closed, the risk was approximately double the day that the windows were open. And we have data over a full pre or asymptomatic period. During this period, the windows were typically open. Again, the top pane showing you people coming and going each of the 5 days. You can see the CO2 that builds up and decays. It's monitored at 6 different locations, and which are at different heights. And we can then see the corresponding risk associated with each of those 6 locations. And over the 5 days, you end up with a likelihood of about 6% that somebody else gets infected if there is an infector. We're doing a lot of work on schools. There's a wonderful data set of CO2 monitored in schools, and thanks to iServe and Monodraft so far, we have some nice data which Caroline Foyer has been analysing, and the results show so far consistently show this is a typical classroom. The R number, the number of infections rising from 1 infected person, and we can see they're a lot lower in the summer months than they are in the winter months. So I'll leave my slides there, my conclusions there, and ask for any questions.
Thank you very much. So Owen, I see we have a couple of questions here.
Yeah, there's a couple of good questions. Henry, do you have any comments on how your estimator for infection differs or is similar to the estimator built by Jose Luis Jimenez?
By the estimator, you mean the spreadsheet online?
Mm-hmm.
I mean, they're both based on the Wells-Riley approach. Ours takes CO2 data rather than needing to input a ventilation rate, which is very useful because it's very hard to accurately measure the time-dependent ventilation rate or outdoor air supply rate more accurately. But it is relatively easy to monitor CO2. That credit for that is due to Rudnick and Milton, not us. Our contribution is really to think about these regularly attended spaces and develop Rudnick and Milton's model so that it can account for the time varying occupancy and activity level.
Okay, two questions sort of together. Sorry, go on.
Go on. One more, I think.
With 2 questions together, which is what is classed as a super spreading event, and do your models include the occupants wearing face coverings?
The first one is not trivial to answer. I can send a long document to someone on that if they are interested. The second is at the moment no, but you can assume some filtration of the particles by a particular type of mask, and that's very easy to incorporate.
Okay, well, I think with that we should move on. So thank you very much, Henry, for that. And we're going to move on now to Clive Beggs from Leeds Beckett, and who's been looking at the scope of UVGI as a mitigation measure. So Clive, over to you.
Thank you, Paul. I'm going to talk about the use of UVC light to disinfect air in the context of COVID-19. Before I start, I'd just like to acknowledge that this is a collaboration between myself and Avital at Queen Mary, University of London. Now, UV light has been used for many, many years, usually at about 254 nanometers wavelength, to disinfect microbes on surfaces, in water and in the air. And when it comes to air disinfection, that was really pioneered by William Wells back in the 1930s in Harvard. And what he was particularly interested in was in TB wards and preventing the transmission of tuberculosis in ward spaces, in hospital waiting areas, and also in homeless shelters. And what he envisaged was using a system very much like this one here in this photograph here, where you have an upper room UV field that's open, shielded from the occupants below, and you're allowing natural air currents to take any pathogens in the air through the field and disinfect them. And when you look at what is actually happening to the DNA or RNA, is that energetic photons of light at 254 nanometers wavelength, when they strike the nucleic acids, they actually fuse together base pairs to form mutations, what we call dimers. And these dimers have the effect of preventing protein synthesis, which is necessary for the microorganisms, whether they are bacterial or viral, to replicate and cause an infection. So effectively, the UV light prevents infections taking place. And it's perhaps worth looking at this point here, comparing SARS-CoV-2, which is the causative agent of COVID-19, with the influenza virus. They're both enveloped RNA viruses, but the SARS-CoV-2 virus has got a genome that's about twice the length. So in theory, it should be more susceptible to UV damage than influenza. Now, if we plot the survival fraction as a log against the UV dose, what we tend to get is an inactivation curve that approximates to a straight line. And if we look at the gradient of that straight line, the so-called Z value, that's the UV susceptibility constant. And that tells us how susceptible the microorganism is to UV damage. And the take-home message here is that the larger the Z value, the easier it is to inactivate the microorganism using UV light. Now, in our study, what we did was we did a literature review of coronaviruses and the susceptibility to UV light. And we compared SARS-CoV-1, that's the SARS virus, and MERS-CoV, which is the MERS virus, to SARS-CoV-2 COVID-19. And if you look at the Z values, you can see that the Z values for SARS-CoV-2 are an order of magnitude larger than the values for the other viruses. So we can tell that this, by the way, was irradiated in liquids. We can tell from this that SARS-CoV-2 is more susceptible to damage from UV light than either SARS or MERS. But of course, we're interested to what's happening in the air because we're air disinfecting here. And unfortunately, nobody has done any work disinfecting SARS-CoV-2 in the air. So we've got to go to other related coronaviruses. And there are actually 3 examples that have been published, 2 of them very recently. And when we look at the Z values of those, we see that they are, on the whole, much greater than for the other comparative viruses and aerosols. By the way, they're much easier to inactivate in the air than in liquids. Notice the relationship between the influenza virus. There's 2 experiments done on this, and it's almost twice as long, which is what you'd expect from the genome being long, almost twice as long as well. If you compare it with Riley's experiments done in the 1970s on Mycobacterium tuberculosis, what you find is that the mouse coronavirus, which we used in our feasibility study, has got almost the same Z value. And so it's going to be as susceptible as TB, basically. So all the evidence is suggesting that SARS-CoV-2 is very susceptible to damage from UV light, and that we should be able to use air disinfection to make a difference. So the question is, how do we use that? Well, I suggest that there are two ways in which it can be used in buildings: induct UV systems and upper room UV systems to potentially mitigate the spread of COVID-19 in buildings. Let's look at the induct systems. These have been around for quite a while, but where I see that these are potentially very good is to actually, as retrofit technologies, to enable buildings that have recirculated air to operate in winter. So if we can put the lamps in the return air, then this may enable the system to operate safely. Let's look at this in more detail. Here we have a generic HVAC system, a mechanical ventilation system. And we often in these systems return around about 50 to 80% of the air in order to save energy, basically. So if you've got an infector down here, a person who's maybe asymptomatic, and they speak or they cough and they produce aerosols containing SARS-CoV-2, these get entrained into the return air ductwork and then get recirculated round and supplied to the rest of the building. In other words, you've got essentially a pathogen distribution system, which is not exactly a very good idea. So what we could do is put UV lamps in the return air duct here. Now, we could put them in the supply air duct. Some people advocate that. But in the return air duct, we've got a number of benefits. We not only disinfect the return air, but also the recirculated air, it protects the filters and the coils in the air handling unit. So anyone doing maintenance on these is protected, and it also protects the exhaust air. And there have been cases with other diseases where people have contracted infections from exhaust air. So that's a big issue as well. But of course, while it's got potential, there's no such thing as a free lunch. The biggest downside is the fact that the air velocities in the ducts are fairly large. And so the irradiation time in the UV zone is around about less than 1 second. So you need very large lamps. And these can often be of the order of kilowatts. And so you have large electrical loads. Also, we have difficulty getting a kind of uniform irradiation dose across the duct. And the problem is that it's no problem if you've got an aerosol passing close to the lamp, but in the corners of the duct, if the path of the aerosol is distal to the lamp, then it may get through without being irradiated. It may still be active. And the problem, therefore, is that we've got to rely on, as designers of systems, rely on the claims of equipment manufacturers. And unfortunately, many equipment manufacturers are sometimes prone to overclaiming and have not necessarily done the adequate microbiological testing, especially for coronaviruses. There's also the problem that these things need to fail safe. What happens if the lamp goes out? How do we know, and how do we make the system safe then? So how does it fail safe? There's lots of unanswered questions, but I haven't got the time to go into them here. So we'll move on to upper room UV. Now, upper room UV, what you're doing is you're creating an open UV field whilst shielding the actual fittings so they cannot be seen by the occupants of the room. And what you're relying on are the natural convection currents in the room to take the pathogens through and have them disinfected. Often you get several passes through here. Now, the take-home message here is that you can get very high equivalent air change rates with this type of system for the target microorganisms. I won't go into the maths that's in our paper, but just to say that we used a complete mixing model, which is a reasonable approximation for many rooms. What we did was we modeled a room with these dimensions here, which were chosen to fit in with the dimensions for a lamp in Mel First's paper. He wrote some papers on guidelines of upper room UV, where you could reasonably expect to get an upper room UV maximum flux of about 50 microwatts per centimeter squared. In the analysis, we used the mouse coronavirus, the Z value for that, as a surrogate for SARS-CoV-2. And we looked at various air change rates, ventilation rates, and what we were looking for was a 90% kill, a so-called D90 kill from the UV system. And these are the results. So these are the expected results with the Z value that we used for the various ventilation rates. And under the worst case scenario of 8 air changes per hour, a ventilation rate of that, we only needed a UV flux of around 8.5 microwatts per centimeter squared, which is well under the maximum flux we could get in the room. And even if we used a worst case scenario where we actually divided the susceptibility constant by 10, so it made it 10 times harder to kill, we still managed to get under that threshold, but most of the time, only at the very highest ventilation rates did it fail. So in theory, upper room UV should be very effective against COVID-19. In fact, we should be able to get effective ventilation rates in excess of 100 air changes per hour in that kind of space. However, the thing to remember is that COVID-19 is not TB. The two diseases may have the same similar Z values, or the two microorganisms might have similar Z values. But TB is a classic airborne disease. It's caused by the transmission of droplet nuclei in the region of under 10 microns size. And when these are inhaled, these 10 micron and under sized particles go down, travel down to the alveoli and cause an infection there. COVID-19 is a droplet-borne infection with much larger, coarser aerosols. We consider round about under 100 microns, but these evaporate very rapidly, as we've heard from other talks, to maybe something less than 50 microns. And at that size, these can easily be taken up by the falling velocity is under 0.1 of a meter per second, the settling velocity. These can easily be caught up in convection currents from thermal plumes from occupants in buildings and be transmitted large distances widely distributed within the room space and taken up into the UV field. But where the problems,
2 minutes,
yep,
Clive.
Yeah, that's okay. Where the problems occur are that unlike TB, where the small droplet nuclei are going to stay with the air current and not decouple, because we're dealing with coarser aerosol particles, if the air velocity drops below a certain threshold, depending on the size of the particle, or we end up in a stagnant region in the room, these particles could fall out, and I signify them here in blue, and drop down through the breathing zone, and therefore these have not received a lethal dose. They've got a sublethal dose of UV, so they still may be active, and they still may pose a threat to other occupants. So what we could do, what we know is we need to get from the work that I did on this years ago at Leeds, and we published in the early 2000s, was that you need to have good mixing with these upper UV fields. And so maybe we want to introduce fans into here. And if we take this further, this is a very nice illustration here. This is from Zhu's work at Harvard and Penn State. And what they did there was they introduced a fan into a chamber, and this is with the fan off. And they looked at the effective disinfection, and you can see that there was in stagnant regions in the room where someone in that region received much less protection than somewhere elsewhere. This was with upper room UV. But when you put the fan on, you've got much better mixing in the space. So the take-home message here is you need good mixing. And the problem is we don't really know how that works yet with COVID-19. So the good news is that UV seems to be able to disinfect SARS-CoV-2 very efficiently. So it seems that UV air disinfection might be extremely helpful in fighting against the transmission of COVID-19 in buildings, particularly in duct UV and also upper room UV. But the jury's out on these areas. We urgently need research to be done to look at the way coarser particles behave in this situation and to see how we can maybe promote the movement to utilize these things. And there's my talk. So thank you very much.
Thank you very much, Clive. We just have time, I think, for one question, perhaps while we change over speakers. So, Owen, if you want to read out one. And,
sure. There's a question from Adrian Sims, who comments that upper room UV requires an empty space at ceiling level to allow the air to move through and to allow the UV to hit that air, whereas a lot of rooms will have building services in that zone. Is that something that's a common issue, the building services getting in the way of where you would put upper room UV?
Yeah, well, you need an open field up there. So I presume there we're not talking about building services that are above a false ceiling. We're talking about building services exposed in a room space that you might see in many retail outfits or in pubs and restaurants and things. Yes, you need a space above the room. Really, I think Melfirst and Asher are saying a minimum height, clear height, the bottom of the zone of 2.1 meters, others are 2.3 meters. But really, you need the kind of 2.5 to 2.7 meters clear in a space. But there are many buildings that have that without services there. We're talking all below the false ceiling.
Sure. Okay, thank you very much, Clive, and it's good to be encouraged, I must say. So we'll move on now to Dara Murnane from the University of Hertfordshire, and his slide is up. So when you're ready, please start your talk. Thank you.
Thank you very much. I'm reporting on the work that's come out of a group of a number of scientists across the UK looking at the inhalation part of disease exposure and transmission. We've also, in the last year, several speakers here are members of a new Centre for Doctoral Training in Aerosol Science. So if the pandemic was ever going to happen at a good time, involving airborne transmission, it might have been this year when the centre started. We have a number of researchers working across this team. The majority of the researchers are focused on computational fluid dynamics and computational modelling systems. Myself and David Sykes are probably the only researchers based from a microbiology or an inhalation component. And really what I'm going to work on and report today is the work that we've been doing around assessing models of inhalation as they might be applicable to bioaerosols and COVID in particular. So if we look at a brief review of what we're talking about with inhalation exposure to bioaerosols, really we're looking at aerosols that cover a wide size range. In aerosol science, we typically take a definition of around 0.1 up to 100 microns as being the size of transmission for aerosols. And when we look at traditional models of inhalation exposure and deposition, we would assume that the particles of the smaller size range can reach the pulmonary region, the deep airways of the lungs, whereas those which are of an intermediate size tend to reach the transmission airways of the lungs, whereas the larger droplet sizes, the wet aerosols or large particle, dry particle aerosols will deposit in the extrathoracic airways and the nasopharynx. So we've got a wide range of particle sizes. And if we think about the process, we have a ventilation process where an individual inhales, then the airborne particles within that air then undergo deposition, following which there's a step of either absorption into the epithelium, which is the biological exposure, clearance from that epithelium, or indeed non-deposited particles will be exhaled back out in the next breath. So really we need to think about factors related to the duration of exposure of an individual, but also the lung volumetric inhalation parameters. We also need to consider the concentration of particles to which that individual is exposed, and we need to consider the size-specific concentration of the viral particles within that aerosol. So we need to also then consider of that aerosol concentration in a particular size band, what is the viability of that virus, and this is going to be related to the dosimetry. So if we look at the classical models for exposure analysis, and really the ICRP model is the gold standard, and based on both computational and empirical evidence. So this was first published in 1994, and really what it provides a way to calculate what the dose risk is for an individual into various regions within the airways, whether these are the extrathoracic regions of the oral nasopharynx, the tracheobronchiolar region, which are really the conducting airways within the lungs, or down into the alveolar region where the gaseous exchange happens. And each stage, then each organic region is treated as being a series of filters, and each filter is an anatomical region, and various calculation parameters based on the mechanics of particle deposition and interception are applied at each stage. to come up with an estimate of the deposited dose within those regions. So one thing that's important to point out now is that we're really limited in the range of regions that we can look at here. So we see the extrathoracic regions, which can be divided up into the nasal or the oropharynx, and the tracheobronchial region and the alveolar region. So we don't really have a great degree of sensitivity in the anatomical breakup there. There are a variety of alternative dosimetry models, but as you'll see, the ICRP model still, in many respects, represents a gold standard because of its basis on empirical evidence. There are a variety of different models based on single particle pathway, stochastic trajectory of the air throughout the lungs, and the behavior of those particles. And what we see is that generally there's a pretty good overlap for the total deposited fraction within the lungs between all of these different models. And we take that as being a good point, because obviously if we can get good overlap between these more advanced models and the ICRP is probably a good starting point with its empirical validation. The problem with this is when we start to look into the regional deposition fractions, there's much less agreement. The agreement between the different models becomes much poorer. And this is a particular issue for us, obviously, with bioaerosols and disease transmission, as we'll see in later slides. So what we're looking at really is an under prediction with the ICRP model of nanoparticle deposition within the upper airways, within the nose, for example. We're seeing a much lower prediction, sometimes as much as 20 to 25% different from the ICRP model for nanoparticles within, 100 nanometer particles within the tracheobronchial region. So there are some problems with those models that still remain to be addressed. In 2014, the US Food and Drug Administration introduced a bioaerosol enhancement model for the ICRP, and in brief, to show the differences, they really started to take into better account bioaerosols, so disease transmission aerosols, so where you could have individual proteins all the way up to rod-shaped bacteria, for example, within droplets. So it enables non-spherical and narrow normal distributions of particle size ranges. So this started to become much more suitable for purified monodispersed bioaerosol exposure studies. And indeed, it's possible to change the particle size distributions of the aerosols to represent what's measured in the environment, but also the individual breathing parameters, age, for example. And this is different to the ICRP model. And in addition to that, because it's associated with risk estimation, the new ICRP model for bioaerosols also provides confidence estimates for the deposition fractions as are calculated. So it is an improvement, but nevertheless has some shortcomings. And these are particularly clear when we look at the issues that as they emerged with COVID throughout from the start of the pandemic. So, for example, the virion clearance and absorption measures differ substantially to the radiochemical aerosols, which don't really dissolve in the original model. There are different aerosol size fractions that respond differently to the ambient humidity, both in the atmosphere and within the lungs. The aerosols which we're currently studying with respect to COVID are highly dispersed. We have some that are very small nanometers, whereas we're also having to take into account larger droplets. And SARS-CoV-2 shows a gradient of infectivity from airway by airway through the different generations as we proceed through the lungs. So we started to look and see what other models would be suitable, and of course computational fluid dynamics provide pretty high level detail, and when we look into this we can see that really the most advanced technologies really are to use CT scans of realistic airways and undertake models of particle deposition within the different regions of the lungs. And there are some questionable assumptions when we look into these types of studies. At laminar flow, such as we see now, we see pretty good trajectories and abilities to start to see where the particles deposit within the upper airways. But when we move on to turbulent flows, such as are more reflective of individuals inhaling with high velocities, or not at rest or undertaking exercise, we can see that most of the CFD that's been completed to date is really on idealized tubes and don't really take into account droplets. So there are solid particles moving throughout. And when we look into the lower respiratory tract, we can see that when we reach the, the beyond generation 13 onwards, really the lower respiratory tract is not a static cylinder. So these assumptions are not particularly correct. And the flow tends to be laminar as a whole, but due to flexing at the walls when these airways expand under the pressure drops of inhalation, and we can start to see that wall geometric features interact with the parameters of gas flow. And this is going to affect how the particles come in contact with the wall of the airways and whether they do indeed experience deposition or not. And when we look at trying to model this, well, we've got a fluid structure interaction problem. So this is a coupled problem where we need to look at elastic solid studies, but also to look at the fluid modeling. And we can see pretty large deformation of the airways, and that means we've got a geometrically non-linear elastic problem. And because they're biological materials, the material characteristic is also quite non-linear. So although conventional Navier-Stokes CFD is suitable for studying the laminar flows which are predicted in these regions, actually they're going to struggle with the grid and boundary conditions, and a lattice-Boltzmann-based CFD approach is probably more appropriate. So if we try to develop this model, then the model which we anticipate using would be a high level, so low fidelity type model that will provide rapid information for potential respiratory exposure for individuals that measure ambient aerosols. So we measure the ambient aerosol properties, and then we can undertake relatively high level assessments of the respiratory exposure. But really what's going to be necessary for a virus like SARS-CoV-2 is an airway by airway deposition dosimetry model that takes into account multimodal and polydispersed aerosols. We're also going to have to improve in the ICRP method of taking into account hygroscopic growth and also work out the lung penetration for different boluses during the inhalation cycle. But we should also be able to provide our virologists and immunological colleagues with a high fidelity model that really describes the process and has a high fidelity calculation of how many viral particles are introduced into different regions of the airways, because in the lower airways, the clearance rate of these particles is much lower than within the upper airways. So what we're suggesting is that we could employ a CFD experimentation model to develop in silico deposition data and compose an enhanced bioaerosol dosimetry tool. And because there are lots of data out there on lung deposition now from the pharmaceutical literature, it would be possible to cross-validate any of those CFD experiments against the publicly available deposition data. So if we think about how this is going to work, well, we have a high fidelity CFD based model. So this is what we call the white box model, where we run airway by airway simulations of particle introduction into the walls. But we use a black box model of advanced artificial intelligence guided experiments to test those data sets. And once we do this, we're able to use the available literature from the pharmaceutical literature to study droplet deposition and nanoparticle deposition within the lungs. So we can combine that then and turn that into a low fidelity white box model, which can be more accessible for individuals to assess risk. So we use that high fidelity CFD to really improve on the shortcomings of these low fidelity white box models. So we end up with a somewhat gray box, which is a physics informed data driven model. You can see an example of the types of things that we're talking about here. So there is a tool available on the web that you could look at to see this, but we can input a variety of parameters such as aerosol properties. We could introduce environment properties and physiological properties in order to generate an assessment of risk and come up with a risk response surface. So in conclusion then, we have clear information that there's respiratory exposure to SARS-CoV-2 containing aerosols. That respiratory exposure containing aerosols occurs for large droplets, which are likely to be in the upper airways, and dry nanoparticles, but we need to improve the inhalation dosimetry assessment to make them more physiologically relevant for bioaerosol exposure.
Thank you. Thank you very much. I think we just have time for one question, Owen.
There is not a huge number of questions come through on this particular talk, but one is about you mentioned CFD simulations and the lack of simulations using turbulent flow. Are there any CFD simulations which have tried to look at the impact of face coverings?
So there have been a number of studies that have looked at the impact of face coverings on the airflow, but this isn't related to the particle trajectories. It looks to see how the ventilation parameters within the upper airways have changed. And this is going to really change the dosimetry of the particles, because we'll move from a turbulent airflow, which is the normal situation, to a more laminar-based airflow with the filter material in place. But the modelling hasn't been achieved yet, and there's really quite poor validation data out there for these CFD models anyway.
Thank you very much. Well, that's a really interesting talk. Thank you. And can we move on now to the final talk of this session by Prashant Kumar from the University of Surrey, who's been leading the group on case studies. So Prashant, over to you.
Thank you very much, Paul. And thank you very much for this opportunity to talk about this Group 7 activities, which we call them case studies. So we start with thanking a lot of people who were involved, in the exercise, from Cambridge, Imperial, a number of the other organizations. So not all the names are there. My apologies if that's the case. So the idea of this the subgroup was mainly to look at all these areas from the lens of real life situations, and also try to understand actually what the industries or the businesses are kind of facing the problems. So it's more of a thinking of a scientific problems which are driven by the the real needs actually at the at the ground level. So we had these weekly meetings, around 55 members. We had a really good representation from different industries, representing supermarkets, school, trains, buses, care homes, hospitals, etc. And I think that one of the underlying kind of the challenges were trying to think of what kind of the challenges are in terms of this 2-meter rule that was there, and then the other things actually we changed over time, which is kind of limiting the occupancy in different places. So so when we started this group, so there was very little in terms of the airborne transmission. So the contact transmission through the direct routes, which is when the people are kind of exhaling and then depositing onto the people, and then the work actually related to the surface transmission, which you saw earlier. So this is like kind of a short range transmission, and then came this aerosol thing where there is still kind of contention between the sizes between the aerosols and the droplets, and which is like a more extended distance and more time. So a little bit of kind of the history. When we started that in April, I remember that there was a lot of debate about it. And I had this article written with Lydia Morowaska. She was also working in parallel with a lot of colleagues actually to kind of take this movement to the WHO, when they had this article published on 6th of July. And after that, I think there was a release from the 10th of July, from the WHO, when they were talking about this airborne transmission. So they're kind of recognizing it. And that kind of boosted a little bit more activity in our group. So we were thinking about about this particular route. And then there were a lot of questions actually which were kind of raised, and they are still relevant, because we got still more questions than the answers that relates to in terms of the residence times of these airborne particles in different spaces, which is mainly driven by the ventilation. What is the intensity of aerosol versus non-aerosol spread, or what kind of the measures could help in terms of reducing the spread? For example, the partnering in the offices or in the restaurants, and what kind of impact actually you're having when somebody's queuing and so on. So I think there were a lot of these questions. I'm not going to read them, so these slides will be there. But in the end, I think this was also a question for us as scientists, that what kind of the full-scale experiments can be done, which can help actually generalize some of the results in enclosed environments. So a lot of activities in this group has been kind of tuned according to those questions, and we have been trying actually to think from the micro scale to kind of macro scale. And there's been a lot of these, the research being set up. So this comes from the Professor Payne and his team, where there's a lot of the CFD activities were set it up in terms of the supermarket, face-to-face kind of, the impact, understanding the flows in the hospitals, airplanes, when people are queuing outside. But at the same time, also looking into what kind of the modeling be done, just considering, let's say, as a small idealized town, and when people are either sitting at home, some are infected, some are exposed, some are the recovered, and so on. So this is still the work which was mainly to kind of combine a lot of this expertise together. For example, the CFD providing either the kind of simulations of the flow, the data assimilation, kind of linking with the field measurements or any data which is there, try to kind of build actually the more realistic models. So some of the work which I've been doing as part of my team was also understanding actually these face masks. So starting with the different the respirator, surgical face masks, the homemade ones. So these were also allowed actually quite a lot of interaction with the different the different people, including some trusts, environmental groups who are kind of interested to kind of understand these things better. And there has been quite a lot of confusion since the beginning about the face mask, and you might have realized that these guidances have been changing. But you might have also seen actually in the previous presentations when people were talking about what will be the risk of in an environment while wearing different type of mask, because all these masks actually they might not do the same thing. They could have a very kind of the different characteristics in terms of the penetration of the particles, or what is their kind of filtration efficiency. But one thing is quite common in them, that they got kind of three kind of layer. The one is more of a hydrophilic layer outside, then in the middle you got the filtering layer, and outside you got more of a hydrophobic layer, which is kind of water repellent. So we had a setup built in my lab where we are looking into the high resolution measurements of particles starting from a few nanometers going into the micrometer range, and try to kind of understand actually what these masks the efficiencies would be, but more importantly try to look from the relative terms. So there is quite a lot of emphasis, and in fact there is a rule actually in different parts of the world, including in England, where you might want you have to have the mask actually when you're traveling, and they call it like a face covering. So people are adopting a lot of these different type of masks which are homemade. So it basically the exercise kind of allowing to understand actually what kind of efficacy it is. But then also there is a point of being uncomfortable, means what is the kind of the pressure drop, because sometimes it becomes really difficult to breathe in when you have this kind of wearing these masks, and the saturation time of them depends what kind of fabrics or what kind of material they are built on. So what we have been doing is trying to kind of understand that what could be the user's time. So this figure is quite interesting in a way. It shows the time on the kind of x-axis, and on the y-axis these are the numbers which are kind of representing the normalized penetration efficiency and the normalized pressure. So in a way there is a point actually which comes when your pressure starts increasing and your penetration efficiency of a mask over the use of time start decreasing. And could this be basically the point where you can say that like this is kind of reaching to a point where you should not be like reusing some of those masks which are being used. There are literature which suggest that you might be looking into around 4 times of the the pressure drop when you can call these the mask being saturation. So I think that a lot of this exercise is driven in terms of understanding these aspects better, but also then informing some of the assumptions which has been kind of considered in different models and in different the investigations. And you saw in the previous presentation when you could see that there is a very kind of high deposition of the particles in less than 100 nanometer range in the in the respiratory system. So I think depending on what kind of size range we are talking about, what kind of mask we are talking about, the risk actually, which we are estimating, could differ quite substantially, and there is quite a lot of the gap at the moment which needs be filling, and then taking basically forward some of those findings into the schools where you saw some work from Henry. There has been quite a lot of efforts we have been kind of putting in this particular area. So this slide comes from Letitia working with Paul and Trace. We are looking into the different scenarios. So we are talking about the occupancy, but you still ask a question in terms of whether the different combinations in the classrooms actually they help actually reducing the spread. And this is a new. I just saw somebody shared with me. In Bracknell School, they have got some cases of this COVID-19, and I think it's quite kind of concerning as moving ahead, as we could clearly see that the ventilation is a key thing basically in this whole game, and the other thing is basically how far apart you can keep people away from each other. And the fact is that when the winters come, then all these things kind of squeezed into a very kind of limited space, and this will be something I think still very relevant, and a lot of questions are there. I mean, how this thing will operate actually without having the big boost in terms of the COVID-19 cases. So, so some of the work that we have been doing was understanding the bits into the trains. So thanks to the first year group, but especially the team, the UKRI project team, which is Cambridge, Imperial, and the Professor Kath Knox, I think she's leading that project on the rail, where we got some opportunity to do some the measurements inside the train cable. So what you're seeing there is basically the different seats, and these different points are showing actually what kind of the aerosol distribution would be. The red one is basically the release of the aerosol, so you can consider that as a kind of a benchmark. That's what is kind of the stabilized as a red pullet. And if you normalize all these concentrations, so each kind of blink is showing around 5-minute average. One of the interesting things you could see in there, that the top case is talking about the ventilation off, and the second case is showing the ventilation on. So when you have the ventilation on, you could see that this green things basically, which is showing the lower kind of level of the normalized concentrations, the risk of getting infected of the people who are sitting next to each other is quite quite low as compared to when you have ventilation off. So it kind of substantiates actually some of those things we are talking about, the ventilation, and the things get really worse when you don't have this ventilation. For example, you could see these bubbles are kind of increasing their concentrations. But this is the very first kind of preliminary kind of region. So we got some preliminary experiments, but there is quite a lot to do in terms of understanding this at a much bigger scale, understanding a different type of the cabins and the different ventilation conditions, and that could also help actually perhaps answer some of the questions in terms of the best strategy, which could allow some of the risk mitigation in these environments.
Just 2 minutes, Prashant.
Yep. So so this is basically the second last slide, or maybe the last one, where I've been teaming up with some of the colleagues from Australia, where we are looking into a systematic review, which is registered with the the NIHR. It's mainly to kind of look systematically in terms of the environmental sampling, the epidemiological studies for the SARC, the COVID-19, the previous version, and the MERS. And the idea here is basically to kind of bring a little more clarity and document actually things in a more systematic way, what's going on in terms of the airborne transmission. Interestingly, the 3 bits actually which helps, and we came up with these kind of things in the very beginning in the April, when this paper, the short paper, was kind of published. We're talking about the role actually of the different people. So I think there is still a need of the building the knowledge to inform the holistic decision making, because we got a lot more questions which are kind of not addressed. There has been a huge amount of progress over the last several months, and thanks to this scientific community who has been working really hard. but then there are still loads of things actually which are needed, and that would allow a better decision making. So we should continue basically this, the effort in the direction to fill those the gray areas. The built spaces remains important, and they will remain important, in future. Until the vaccine is there, and that I think includes the ventilation and the occupancy, which has been kind of highlighted quite a few times, but also the public, there is a role there in terms of the face mask and and kind of taking the right decisions at the right time. So those things can be kind of avoided. So with that, I would like to thank all the team, the collaborators, the funders, and
can I jump in with a couple of questions, Prashant? We've got a couple of good questions. The first is, when you were looking at the face masks, did you assess the performance with and without nose bridges, and what was the impact?
That's a really good question. So we have just started setting up those experiments. So I expect that there will be quite the big difference in terms of understanding the leakage effect, which we haven't really done so far.
Okay, and the second question was in relation to this. In relation to the schools, you showed a number of seating layouts. Which seating arrangement was better?
So this is the work basically which is still being set up. So the simulations has not been yet carried out as far as my understanding is concerned. But this is something which is in plans, and we are waiting actually for some of the some of the decisions to be made, so we could allow continuing actually the research. We kind of try to set it up through this the task force duration.
Okay, thank you very much. Well, that brings us to end this first session of this meeting.